So for this lesson, we are doing some problems on confidence intervals for differences, plus we're actually doing a healthy amount of practice for correlation and regression, which was the unit before sampling distributions. First question, in a simple random sample of 300 elderly men, 65% were married, while an independent SRS of 400 elderly women, 48% were married. Determine a 99% confidence interval estimate for the difference between the proportions of elderly men and women who are married. So confidence interval is your point estimate plus or minus your margin of error, and you can see that's kind of the format we have here. You can see the plus or minuses right there. So it's not the lower boundary, upper boundary in parentheses format. It's this format here. Now, since we're dealing with proportion, since we're dealing with proportions, we use z's for our critical values, and we have our standard error, so we multiply those two to find the margin of error. So the general format for a confidence interval for a difference in proportions, there is your point estimate, our statistic here, our critical value, and our standard deviation, which is messy because we're looking at the difference of two proportions. Now we can already see a few don't match. For example, this one has no square root, so let's mark that one out. This one, we're not supposed to be dividing by 2, so cross that one out. And then this one, we do not have the correct value. You can't just this is kind of weird. You don't have the right format that matches over here, so we're crossing that one out. So because the confidence level is 99%, our center area is 0.99 and our left area is 0.995. And you're like, what are you doing, Mrs. Everman? Well, I'm talking about this one for older calculators, so let's do that. Okay, so we're going to play again with finding critical values for confidence intervals with proportions. We're using Z star, so I have the normal distribution. Mean is 0 and standard deviation is 1. So this is a standardized form. And what we're trying to do is do a confidence interval, so I need to find a value corresponding to an area, and I want central. All right, now you're probably going, Mrs. Everman, why are you using Statlet? Well, because I need to show something for people with old calculators. So this is pretty straightforward, and I'll show the calculator. To do that, you would say, oh, my area is 0.99, my mean is 0, my standard deviation is 1, and here you can see that the critical values, they're the same here. It's because I'm using standardized normal. These are z-scores here and here. All right. So remember this number, 2.5758. All right. So if you have an old school calculator, you only have this option. Okay. So let me hit left. All right. And if I did that, remember that number right there, it's going to change. It's giving you 2.3623. Why is that? It's because it shifted over here. Now we have 1% of the area, whereas before, what percent of the, 1% of the area is over here, whereas before we had 1% split between the two sides. So for old calculator people, how do you fix that? Well, you want this to be 0.5% of area. So you want, you're going to say left tail because that's all your calculator does. So instead of having 0.99 to the left, you're going to have that 0.5% plus the 0.99. So you change this to 0.995. All right. So first of all, let me show you what it's going to do if you don't make that adjustment. And then let's make the adjustment. So we put that extra 0.5% that slid over here back over here. And now I get the right number. So again, older calculators have left side only. You can kind of think about it like doing it like normal at the beginning, central, right? One more time, this is a tricky concept, so we're going to play again. You got 99% here. You have 0.5% here, 0.5% here. But you're only allowed to say left. You can't say center. So left of here is 99.5% because we got to include that 0.5% there, and it will work. If you have the newer calculators, congrats. All you have to do is central and 0.99, or maybe use one of my calculators when you're taking my test or the AP exams. Okay, so now that I talked about the setup on the Staplets, let's get to the calculator because I'm going to cut you off on that normal distribution tablet because we need to start using our calculator. So we're going to hit second distribution, and I'm trying to find a critical value. So if you hit normal CDF, enter, it's like, oh, where do I put my area? There's no place there for the area. So you know you're in the wrong one. So hit mode clear, go second distribution, you might say second bars, and we want inverse norm CDF. And our area is 0.99. If you have the beautiful calculator, you're like, oh, yes, that's center. And then there's my value. Use the positive one for the critical value. No reason to throw an extra negative to make our math hard. For those with the old school calculators, so you go inverse norm, enter, and make sure that you, you would have the left because you don't see these options. It's defaulting here. So you have to go back up here again and make your adjustment. You have an extra 1% on the outside. So there's 0.5% on the left. So you add that 0.5% right there. And then you come in and hit enter. Personally, again, I think it's better to use the newer calculator so you don't have to confuse yourself with that extra math. And that should give you the correct z-score. Okay, so we're going to... So now we have our z-score of 2.576, right? And we're just down to 2 options, and you can see only one of these has 2.576 on it right there, and that is the correct answer. Question 2. So yes, we are pretty much using the same formula as in question 1, which is your statistic plus or minus C star times your standard error. We're looking at a difference in proportions. So it is the same formula. And we're going to memorize, by the way, the confidence level for 95%. You should just have that memorized. It's 1.96. Now, if you're using your calculator, remember your central area would be 0.95. and your left area would be 0.975. So we have the 1.96 here, and we put in all these values, and then we pretty much just go ahead and calculate, and we get 0.186 plus or minus this times that number right there, or 0.115. I'm also going to show you how to do a confidence interval on the calculator. Okay, so let's go ahead and find our critical value again, second distribution, inverse norm, and since we're doing a 95% confidence interval, you should have this totally memorized that this critical value is 1.96. If you're using the new calculator, make sure it's center, which most of you are using, hit enter, and there it is, 1.96. Again, always use the positive one. If you're using the old calculator, you have to adjust that area because that's center, and old calculators only do left, right? So that means I have 5% that's split between the left and the right, 2.5% on the left, so I need to add 2.5% to that 95%. So make it 0.975, and you will get the same 1.96. And while I'm at it, let me go ahead and show you how to do a shortcut for doing confidence intervals straight from data. So this is a 2-prop z interval, 2 proportion z interval. Okay, hit enter. And I can actually put in my values. So we have 210 of 361. Isn't this cool? Enter, 361. Now, you're going to see what format it gives it to you in. Give me a second. 34 and 86. Oops, not 5. 86. One thing, if you're using this, these all must be integers. So hit calculate, and there you go. It actually does all your p-hats. 1, your p-hat 2. What it does not do is it does not give you that format of your point estimate plus or minus your margin of error, which is what the answer is asking for on this problem. Could you go backwards and find it from there? Yeah, you could. Although it's honestly not that horrible to calculate it by hand. Remember, your point estimate is the midpoint of these two numbers, so you add up 0.07 and 0.30, and then you get 0.37, and then you divide that by 2, which would get you your 0.186. And then you'd say, okay, what's 0.186 minus 0.07 to get the margin of error? So it's possible to use this in this question. It's just a little bit of work to do it. So now we have the 1.96, which we calculated for the critical value, and there is our confidence interval, and there is our answer. Problem 3. A researcher plans to investigate the difference between the proportion of psychiatrists and the proportion of psychologists who believe that most emotional problems have their root causes in childhood. How large a sample should be taken, same number for each group, to be certain, 90% certain of knowing the difference within plus or minus 3%. So this is the formula. We're doing a difference of two proportions. Margin of error, let me go ahead and get my pointers. Margin of error equals your critical value times your standard error. Okay, looks ugly, doesn't it? Now, but they did say same size sample, so N1 and N2 are the same, so just use N. Now, we have no proportion to start with. We use 0.5. If you don't have a single proportion, we do the worst case scenario, which is 0.5. Why is it worst case? Because that gives us the widest standard error. And if you'd like to see more on that, look at your notes for this lesson, for the previous lesson, actually. So we're going to go ahead and substitute in the 0.03, the 1.645, because that's your critical value for 90%. We did that on one of the earlier problems. Remember, that's inverse norm. 0.90, 0 and 1 for your mean and standard deviation, center area, okay? If you're doing old calculator, guess what? It's going to be 0.95. That would be the left area. So that's how we get the 1.645, which we've already done this lesson. So, and then once I add these up, basically you get 0.25 up here, 0.25 up there. You add them, you get 0.5 over n. So this is probably one of the most algebraically intensive type of problems you're going to have in AP Stats, where you have to figure out sample size. So now that we have these two together, I'm going to square both sides, so everything is squared. Since I have a square root on this, this just pops out. I have 1.645 squared, I have 0.03 squared. Squaring that, we get 0.0009 equals this ugly number over n. So I squared my 1.645 and then multiplied it by 0.5. Then we can just multiply both sides by n, divide both sides by 0.0009, and I get 1503.347. Now, weird thing about these sample size estimates, your answer will, even though you're like, hey, that rounds to 1503. You never ever round down, even though it's closer to that 3. You always round up because you're saying the minimum sample size. And 1503 really isn't quite the minimum. You need another third of a person. But since we don't want to do that, chopping up people, not good, we round up to one more extra person to 1504. Number 4. In a New York Times poll measuring a candidate's popularity, the newspaper claimed that in 19 of 20 cases, its poll results should be no more than 3 percentage points off in either direction. What confidence level are the pollsters working with, and what sample size should they obtain? Okay, confidence level should be pretty straightforward, right? And that would be 19 out of 20, they get it right, okay? And that's within their range. So that's 0.95, also known as a confidence level of 95%. So we have memorized, hopefully, that the critical value for a 95% confidence level is 1.96. Now they said, what sample size should they obtain? Well, we're going to go ahead and calculate that. So that's margin of error, because we know we want a margin of error of 3 percentage points. So I need to go ahead and find my standard error, which is this formula here, because we're doing just one proportion. So that's the good news. We don't have the really ugly, messy one. And we're going to just substitute in here. Now we know this is 1.96. We know this is 0.03 because they say no more than 3 percentage points. And so since we don't know p hat, right, We don't have anything to start with. We're going to assume worst case, which is 0.05. So I'm going to put 0.05 in both spots. 0.05 and 0.5, not 0.05. 0.5 here, 0.5 there. 1 minus 0.5 is 0.5, so we have 0.5 times 0.5. So I have 0.5 squared on top, which, by the way, I could just say, oh, that's 1.96. Square root of 0.5 squared is 0.5. Then you have square root of n underneath. Multiplying these two out, we get 0.98 times square root of n. So now I'm going to kind of ignore these middle portions. I can multiply both sides by square root of n. So I get 0.03 times square root of n equals 0.98. Divide both sides by 0.03. Square both sides. And I have 1067.11, also known. We got to round up, even though you're like, wait, it's closer to 1067. Well, 1067 isn't quite enough, so we need one more person. And that was it. So your answer is 1068, 95% confidence level. Number 5, a sales representative wishes to survey her client base of 47 companies. She has 47 business cards, all of identical size from her contacts in the companies, and decides to drop them all in a small box, shake them up, and reach in to pick 5 cards for her sample. This procedure is an example of which type of sampling? This looks like throwing things in a hat and mixing. It's pretty much the definition of simple random sample. Nice, easy one for you there. Number 6. When a set of data has suspect outliers, which of the following are preferred measures of central tendency and variability? Well, we need to use measures that are resistant to outliers. Both median and IQR are resistant to outliers. We learned that in our very first unit. And outliers are included in the calculation of mean and standard deviation, which is why those are not resistant. So we would rather use our median and our interquartile range for spread. Number 7. The Air Force receives 40% of its parachutes from company C1 and the rest from company C2. The probability that a parachute will fail to open is 0.0025 or 0.002. Still seems kind of high to me. It's kind of scary. Okay, depending on whether it is from company 1, C1, or company C2. I think I'd rather buy from company C2. Anyways, so if a randomly chosen parachute fails to open, what is the probability that it is from company C1? Okay, so we know that 40% of the parachutes come from company C1. Good, I'm glad we get more from C2. All right, so we're going to have 40. I'm going to make up a big number and create a table. So I'm using one strategy. I'm also going to show you the tree diagram strategy. So I'll say, hey, we got 100,000 parachutes. All right. So 40% come from C1. That means I have 40,000 come from company 1 and 60,000 from company 2. Then I can go ahead and calculate what percent of C1 fails, what percent of C2 fails, and that gives me a total for what percent fail. So here we said 2.5% of company 1, 2% of company 2. So we have 100 and 120. So the probability that it is from company 1, given that it fails, is the probability that it's from company 1 and fails over just the probability of all the failures. Because remember, there are 220 total parachutes failing out of 100,000. Still seems high to me. And we know that 100 times out of those 220, it will be company 1. So you divide that up and you get 0.4545. All right, so you know that's the answer, D. Now let's go ahead and do this with a tree diagram. So first thing we have to do, just like before, you got to deal with the companies because 40% of shoots come from company 1 and 60% from company 2. So I go ahead and start my tree diagram. Then company 1, we know this percent fails for company 2. So the probability that a parachute is from company 1 and fails is just multiplying these two probabilities. So it's 0.001. And you're probably going, Mrs. Overman, that's not the answer. You're right. We'll finish. So I still need to calculate the probability that the parachute is from company 2 and fails. So I multiply these two numbers out, and I get 0.0012. So the probability that a parachute fails in total are these two put together, and we'll just figure out what proportion is this of the total. So the probability that company 1 it's from company 1, given that it fails, is the probability that it's company 1 and fails divided by the probability it fails. Remember, this is on your math chart on the front. So when you do 0.001 over the sum here, you get the same answer, 0.4545. Number 8. 4 data points are used in determining a regression line, y hat, or a predicted y, equals -2 plus 6x. If the 4 values of the independent variables are 37, 52, 18, and 23 respectively, what is the mean of the 4 values of the dependent variable? Okay, so first of all, we created these to, we use these to create our regression line. We just don't know what the what the y's are. And so they haven't told us that, right? So we want to know, what is the mean y? We can find the mean x, and the regression line must go through the point, the mean x and the mean y. So the mean x, I just add these up and divide by 4, 32.5. So you might be saying, oh, there it is. There's the answer. Actually, that's the mean x, and they're asking for the mean y, which, remember, x is the independent variables, y is the dependent variables. All right, so now I'm going to go get my regression line, right? And I'm going to substitute in the mean x, which means it needs to spit out the mean y, which is 193. One of you said, I don't understand why on the last one it asked for the mean, but the answer is way bigger than the numbers. Again, these are the mean x's. It's asking for the mean y. And y is always going to be bigger than x, if, well, you know, pretty much on the positive side anyways. If you're multiplying x by 6 and then subtracting just a tiny 2. So if x is 10, this is like 60 minus 2, 58. So your y is being way bigger, 58, for a given x, at least on the far right side, which we are. We're pretty far right. If you go left, it changes, obviously. Okay. Changing from a 90% confidence interval estimate for a population proportion to a 99% confidence interval estimate, with all other things being equal, in particular, sample size and standard error. Let's see. Will increase the interval size by 9%, decrease the interval size by 9%, increases the interval size by 57%, or decreases it, or we just don't know. So the width is very much proportional to our margin of error. In fact, it's exactly twice the margin of error. So I don't have to do the whole width. I can just look at margin of error, all right? And margin of error is critical value times standard error. So how do we find the critical values? Well, for the 90%, we do inverse norm. Our center area is 0.9. Our mean is 0. Our standard deviation 1 is, and we want center. Remember, for the old calculators, you need to do this adjustment. You have 10% left over, throw half of that onto there because that's the front half, all right? So that's 1.645, and then, oops, that's supposed to say 99%. Pretend that says 99%, and this one will be 2.576. So let me go ahead and show you again how to do this on the calculator. Okay, so we're going to find the critical value, which we do by going to inverse norm. Gives us backwards the value from a percentage. And we're trying to do a confidence level of 90%. So 90% would be in the center. So if you have the luxury of having a nice calculator, one of the newer ones, or borrowing one of mine, you have the 0 and you have the 1. And then you have center right there. Hit enter and come down. And you can see the critical value is 1.64, or you could say 1.645. All right. Now, the other way, again, for older calculators, we're going to practice this a bit on this lesson. If you don't have the luxury of being able to set center down here, if you don't see center, that means it defaults to left. It's working on percentile. So the center area was 0.9, which means I have to have 0.05 on the left, 5% on the left, and 5% on the right. So if I take that center area plus the leftmost 5%, that gives me 0.95. And that should give me the exact same critical value. And again, on the older calculators, you won't see the left option. I'm just showing you the number you have to put in. And you can see you're getting the exact same value. We also need to go ahead and do this for a 99% confidence interval, so second distribution, inverse norm, and for if you're doing it left set, so you have 99% in the center, right, 0.99, and then you have 1% left over. There's another 0.5% on the left, right? So we put that all on the left if you have the left setting. Again, this is primarily for people with older calculators, all right? But much easier if you have the newer calculator and you're like, oh, I'll just say the center area. Oh, it's just 0.99. So 0.99, and then say just center. Voila. So again, I strongly recommend when you're taking your AP test, use my calculator if you can, so you don't have to do this weird mathematical adjustment for the left-handed area. All right? So we have margin of error for the 90% is one, I'm sorry, not margin of error. Critical value for the 90% is 1.645. Critical value for 99% is 2.576. Now, if you're trying to figure out percent increase or decrease, we're going to go ahead and calculate our new margins of error, so to speak, but I'm just going to have standard error right there, right? So I'm trying to figure out how much bigger is this than that. And we're doing percent increase. The way you do that is you do your new value over your old value. We're going to change it to a percent and subtract 100%, okay? So that means margin of error 2 over margin of error 1, and then I put in the 2.576 standard error, 1.645 standard error, and remember, all other things are equal. These are the same standard errors. They go away. So I'm going to get 1.57, which I'm just going to change to a percent here, subtract, and that gives me 57%. So I have an increase of 57%. And hopefully you saw that that is an increase right there. This is bigger than the original value of 1.645. Number 10, as reported to CNN in a May 1999 national poll, 43% of high school students expressed fear about going to school. Which of the following best describes what is meant by the poll having a margin of error of 5%. So, by the way, I'm going to accidentally mark the correct answer right away. So how do we get there? Well, for part A, we're fairly confident the true value is between 38% and 48%. It's not that it's like shifting around, but it's odds are that's where it's at. It's not really a probability. It's just our confidence level. So that one is true. B, 5% of students refuse to participate in the poll. That has nothing to do with non-response, all right? So margin of error is in the range that you're setting for capturing the true value. Part C, between 38 and 48% of those surveyed expressed fear about going to school. Actually, exactly 43% expressed fear. That's what your survey says. See, it's up there. It's your point estimate. So that we know the number from our sample. We're not having to guess the number. The point estimate is known. So that one's false. Then the margin of error is, so they said there's a 0.05 probability that the 43% result is an error. Margin of error has nothing to do with probability. And then finally, if similar size polls were repeatedly taken, they would be wrong about 5% of the time. This is more about confidence level. So if I had a 95% confidence level, this would be appropriate, but that's not what we're talking about. We're not talking about a 5% or 95% confidence level. We're talking about a margin of error, which is our plus or minus. Number 11, suppose that the regression line for a set of data y hat equals mx plus 3 passes through the point 2, 7. If x bar and y bar are the sample means of x and y values respectively, then the equation for y bar is what? So first of all, we're going to substitute into the equation they gave us. They told us that there is a point 2, 7 that it passes through right there. So I'm going to put 2 in for x and 7 in for y. Then I'm going to subtract 3 from both sides. And so I find out my slope is 2. So my equation is y hat equals 2x plus 3. Well, if they want to know y bar, all I have to do is replace that and change it with x bar there, and then that gives me y bar. So the correct answer is D. Which of the following is a correct statement about correlation? So this one's a pretty deep one. Get ready. If the slope of the regression line is exactly 1, then the correlation is exactly 1. So first of all, let's look at that equation, the formula. Slope and correlation aren't usually equal to each other. You see there's a standard deviation or error in y over standard error in x. So that is not typically 1. All right, so slope and correlation aren't usually equal to each other. Besides, correlation has an upper limit of 1. Slope could be 1,000 for all we know, right? And our lower limit for correlation is -1. Slope could be -50. So correlation is limited to be between -1 and 1. Slope is not. Okay. Then the next one says, if the correlation is 0, then the slope of the line is undefined. No, actually it's just 0, because if you put 0 in here, oh, you get B equals 0. Now, let's go ahead and look at part C. Let me actually go back a second. Switching which variables called x and y, which is called y, changes the sign of the correlation. So we'll play with Staplet. So I'm putting some values in. I just made up a relationship. I have x and I have y, and I begin my analysis. And there's my scatter plot. And I'm going to go ahead and calculate my correlations. Just hit calculate there, and you can see it's 0.9928. So what I'm going to do now is I'm going to switch these so you can see the impact. Yes, that's fine. I mean to switch it. And I don't need that one. There we go. So this is, I'm taking the data and I'm switching x and y. So now I have y here. I have x. And I hit begin analysis. And you can see it looks a little different. It's close, but I have exactly the same correlation. So hopefully you should have remembered when we did this for Barbie bungee jump, switching the x and the y, it changes the equation. I'll show you. So here's the equation. Here the slope is 0.4841. Go take these values again, Control X, and yes, I'm going to put a little space there so it's easier to copy that. Control X, put those up there, and then switch back my X and my Y. Remember our slope was 0.4848, and you can see that when I calculate it, the slope's a little different. Oh, now it's more like 2. So again, but the correlation, the actual correlation is exactly the same. So slope will change, intercept will change, but not the correlation when you switch variables. So since there is no change in correlation when switching variables, part C is false. Now we're going to look at this next statement. So this one's a little deep. The correlation R is equal to the slope of the regression line when z-scores for the y variable are plotted against z-scores for the x variable. So I'm actually pulling out what I did for the notes. This should have been the F3 notes when I'm talking about regression to the mean. So standard deviation or z-scores comes up in that.
Okay, so in this applet, I have several points, A, B, C, D, E, and I have this automatic regression line that's calculated. No matter where I move the points, the line adjusts. And you can also see the correlation, which is -0.72. And here we have the formula for slope on your math chart. That's called B instead of M. And there is the standard deviation of Y and the standard deviation of x. So it's automatically calculating those. And you can see here is the mean point. So the mean x value is 3.86, which is right there, and the mean y value is 2.98. Now, in this formula, what I actually did is I have the point slope form, which you might remember from geometry, but you can work this out with just having the, and determine the equation by just using the formula on your math chart, which I will show you in the notes. But so here we go. The main thing is as we move these, you can see here's the slope for the original line, and this is the slope for how many standard deviations y is compared away from the mean compared to x. So if I take this point C1, it is about, actually let's take this point B prime. B prime is roughly -1 standard deviations from the mean value of x. So that means we would expect the y to be about 0.72 standard deviations above the y mean. All right, you're probably going, wait, but it's below. Well, that's because the line is not a perfect fit. And so you can see here it's actually a little above, and there it's a little below for the actual points. All right. So the actual points can vary a little more like they actually do in the data. But the line itself, what it's going to use to predict the values, it's going to vary like this. So even if I pull a point way away, let's say I put all these points together, all right, we're going to get a nice correlation. So this one is about 2 standard deviations away from the mean on the x value, and it's about -2 standard deviations from the mean on the y value. And you can see that the predicted value in this case is going to go to -0.99. In fact, the strongest I can make this is making a correlation of -1. The predicted value for y will never vary more in standard deviations than the predicted value for x. Okay, so
So again, let me just point out, this is the slope of the line when I have z-score. So this A prime is the z-score for x and y for point A. This D prime is the z-score for x and y for point D. You can see that D is above average, so it's to the right. It's also below average, so it's below. So this slope right here is R. See how it matches the R right there? And that is equal to the slope of the regression line when z-scores for the y variable are plotted against z-scores for the x variable. So there you go. That one is true. And then finally, there are no units for correlation, so E is false. The correct answer is D. Number 13, a study is made to determine whether more hours of academic studying leads to higher point scoring by basketball players. In surveying 50 basketball players, it is noted that the 25 who claim to study the most hours have a higher point average than the 25 who study less. Based on this study, the coach begins requiring players to spend more time studying. Which of the following is a correct statement? While this study may have its faults, it does prove causation. Well, first of all, it's talking about causation. Is this an experiment? It is not an experiment. A and C. C says, well, this is a controlled experiment. Both of those are false. They're not an experiment. So then there could be other confounding variables responsible for the seeming relationship. So maybe students have more time who have more time to study may also have more access to resources, and which lead them to have a higher point average. Who knows? All right. In part D is just funny. To get the athletes to study more, it would be more meaningful to have them put in more practice time on the court to boost their point averages. Wouldn't that be nice? As high point averages seem to be associated with more study time. And E, blinding's kind of hard in this scenario because the players know how many points they're scoring and they know how many hours they're studying. So we're going to stick with B. There could easily be a confounding variable responsible for the seeming relationship. Last but not least, problem 14. 2 random samples of students are chosen, one from those taking AP stats classes and one from those not. The back-to-back STEM plot below compares GPAs. Which of the following is true about the ranges and the standard deviation? So I'm going to go ahead and calculate the range. Range for AP is 41 minus 23, right? And let me go ahead and get my laser pointer so I can show you. There we go. So you got 41 right here. Remember, this is written backwards. So this is the beginning digit. That's your 10 stem. 41, 23. Subtract those two, you get 18. Here, this is normal. So this is 38 minus 18. We have a range of 20. So Actually, A and B are both false because it says that the first set has a greater range. Now, we know the second set has a greater range, right? So we're pretty sure it's not E either, by the way, because it says they have equal ranges. So we're down to between C and D, which is on standard deviation. Well, they're roughly the same spread, but the mean for this one is going to be a little bit higher than, and this mean is probably going to be more centered. So the mean's going to be a little bit skewed, actually this way, above the median, further above the median or below the median, depending how you're looking at it. So since it's more skewed, we're going to have greater differences and a higher standard deviation. So the answer is the second set has both a greater range and a greater standard